Hey everyone, and welcome to this Grade 8 Geometry Explainer. If you're a focused learner looking to master the exact mathematical rules of how dimensions change when shapes grow or shrink, you are in exactly the right place. Today, we're taking a really fascinating journey from one-dimensional lines all the way into three-dimensional space to uncover the secrets of scaling similar solids. Okay, let's dive right in. Here's our roadmap for today. 1. Similar solids and dilations. 2. Surface area, squared rule. 3. Volume, the cubed rule. 4. Comparing scaled solids. And finally, a recap and transfer question.
Section 1. Similar solids and dilations. First things first, before we can actually scale anything, we have to establish what makes two geometric shapes similar in the mathematical sense.
When we talk about similar solids, we mean solid geometric figures that have the exact same shape, just different sizes. Think of it literally like zooming in or out on a 3D model on your computer screen. The angles don't change at all, and the proportional relationships between the side lengths are perfectly preserved. This resizing process is determined by a specific dilation, which is driven by a number we call the scale factor. Now, it all starts in just one dimension, with the linear scale factor. A linear measurement is a 1D measure, like stretching the length of a single line segment or measuring one edge of a cube. When we apply a linear scale factor, we're basically just taking that 1D length and multiplying it by a constant value. So if our scale factor is 3, a line that's 2 inches long simply becomes 6 inches long. Easy enough, right? To ground this a bit, let's look at this quote directly from the educational standards. It notes that similarity transformations formalize the similarity ideas of same shape and scale factor. The scale factor is basically the rigid mathematical rule dictating exactly how much our base one-dimensional shape is going to expand or shrink. But what happens when we move beyond a simple one-dimensional line? That brings us to section 2, surface area squared rule. Let's see how this builds as we step out of 1D lengths and expand into two-dimensional space. So once we have a solid, we gotta think about its surface area. By definition, surface area is a two-dimensional square measure representing the total area of all the faces on the outside of a solid. A great way to picture this is the exact amount of wrapping paper you'd need to perfectly cover a box. Because we're covering a flat surface, even if it's wrapped around a 3D object, we are fundamentally dealing with just two dimensions, length and width. And that brings us to the squared rule. Because surface area is a two-dimensional measurement, any linear scale factor we apply to the solid's edges doesn't just multiply the area by that scale factor. No way. Instead, the scale factor actually has to be squared to find the new surface area. If you scale up the length and you scale up the width, you are literally multiplying the scale factor by itself. All right, I want you to actively think about this for a second. Here's our first pause check. What happens to the total surface area of a shape if the one-dimensional side lengths are multiplied by a scale factor of 4? Take a moment and apply that 2D logic we just talked about. If you said 16, you hit the nail on the head. Because surface area exists in two dimensions, we square that linear scale factor of 4. 4 squared is 16. So the new surface area isn't just 4 times larger, it is a whopping 16 times larger than the original. Section 3, volume, the cubed rule. Now we're taking the ultimate leap. We are climbing from flat 2D surfaces into the deep, immersive 3D space of volume. Volume is a whole different ballgame compared to surface area. It's a three-dimensional cubic measure determining the total amount of physical space contained completely inside a solid figure. If surface area is the wrapping paper on the outside, volume is the actual stuff packed inside the box. And to find it, we're dealing with 3 dimensions now. Length multiplied by width multiplied by height. So here's the absolute crucial point. Because volume incorporates 3 dimensions, our simple linear scale factor must be cubed. Think about it. You're scaling the length, you're scaling the width, and you're scaling the height. That is the scale factor times the scale factor times the scale factor. Let's do our second pause check to really lock this in. Imagine you have a solid figure, and you apply a linear scale factor of 2. Basically, you're doubling the length of all its edges. What exactly is going to happen to the volume of that solid? The answer is 8. Here is the immediate mathematical reasoning. Because volume is three-dimensional, we cube the scale factor. 2 cubed is 2 times 2 times 2, which equals 8.
It's kind of mind-blowing when you think about it. Just by doubling the lengths of a solid's edges, the actual space inside becomes an incredible 8 times larger. Section 4. Comparing scaled solids. This brilliantly illustrates why understanding these dimensions is so powerful. Let's look at exactly how these rules play out when we put the math side by side in a created comparison.
Let's look at a simple 1-unit cube. Its surface area is calculated as 6 times its side squared, giving us an area of 6. Its volume is its side length cubed, which is just 1. Now let's say we apply a linear scale factor of 3 to create a 3-unit cube. We plug 3 into the surface area formula, 6 times 3 squared. Well, 3 squared is 9, and 6 times 9 is 54. Notice the relationship there? 54 is exactly 9 times our original surface area of 6. That's our scale factor of 3 squared. And what about the volume? We plug 3 into the volume formula, which is 3 cubed, giving us 27. The volume went from 1 all the way to 27. That is our scale factor of 3 cubed. The math just perfectly backs up the rules.
What's really interesting here is how this progression elegantly visualizes everything we just proved. In 1D, for length, the measurement simply multiplies by our scale factor. Let's call it x. In 2D, for surface area, the measurement multiplies by x squared. And in 3D, for volume, it multiplies by x cubed. It's almost like a universal master key for scaling any similar solid. Section 5, Recap and Transfer Question. We've covered some fantastic foundational geometry today, so let's bring it all home by recapping what we've learned, and then I've got a final challenge to test how well you can transfer this knowledge to a totally new shape. Here are your main takeaways. First, linear scale factors strictly dictate one-dimensional changes, like the length of an edge or a radius. Second, surface area is always a 2-dimensional measure covering the outside of a shape, so the scale factor applied to it must be squared. And finally, volume is a 3-dimensional measure filling the inside of a shape, meaning the applied scale factor must always be cubed. Now for a transfer question to really leave you thinking. We mostly used cubes today, but what if you double the radius of a perfect sphere? Exactly how much larger will its surface area and its volume become? Well, think about the formulas based on our source material. A sphere's surface area is 4 times pi times radius squared, and its volume is 4/3 times pi times radius cubed. Since those variables are squared and cubed in the very formulas themselves, the exact same scaling rules apply to curves. Doubling the radius will multiply the surface area by 4 and the volume by 8. Geometry is incredibly consistent for sure. Thanks for joining me on this explainer, and keep exploring.